And let's see here. Um, basically, as you may have seen in training kit already, but basically we've got iterative sorting today, and today's actually a really fun day, and in my opinion, is not a super difficult day. So I think we can all come into a Monday and be relaxed and just enjoy the content that we go through today. Tomorrow, if you're still struggling with recursion, it can be a little bit more difficult. I wouldn't be worried about it though at this point. You dealt with the stack last week, so you've got a good understanding of what a stack is and how to interact with it. Well, that's the call stack that recursion uses. And then you also use some recursive methods on your binary search tree. So I think you've got a better start than you may have realized if you're still worried about recursion. And then the last 2 days, module 3 and 4, we take the same set of problems like algorithms, code challenges, like whiteboarding type problems that you might see in an interview setting. And in module 3, we go through and get a first pass solution for those. And that means we go through U, P, and E for those problems. And then module 4, we have the same problems and you have your solution from the previous day. And then we just go through R of Ooper and you improve those solutions. So conceptually, this week is actually there aren't a lot of new concepts that we're throwing at you. Like last week where we were learning about all these actual different data structures and what they were and how they worked. This week is more of a practice week for Ooper. So this week it's going to be important for you to really integrate Ooper into your workflow. And the more you kind of commit to, I'm going to use Ooper as a problem solving framework to help me, I think the better this week will go for you. Okay, let's see here. I will set a timer for 25 minutes. And when this timer is up, we'll take a 5-minute break. And please, just like last Thursday, just call me out in Slack if for some reason I missed that. It looks like we've got a question that came in on Slido already that says, can we review logarithmic runtime? I have trouble understanding how that works, and we will. That's actually one of the first things on the agenda today. So thanks for that question. All right, so as far as for today, what we're going to cover is we're going to revisit runtime complexity. So we covered this on Monday of last week, but we covered it like in just enough detail to be able to describe the runtime complexity of the different methods on the data structures we were working with. We'll look at that a little bit deeper. Then we have linear and binary search, and then we'll talk about some of the classic iterative sorts, and we'll go through insertion sort together. One more housekeeping thing is, it was asked in the help channel, which was a great question of, hey, I noticed in training kit, we're covering these different iterative sorts, these classic iterative sorts, but there isn't like a code or solution or pseudocode for all of them. So the idea is that for today, like we'll go through together insertion sort, and we'll go through U, P, and E of that. And then you'll use that workflow and that practice that you got during the guided project to go over the other iterative sorts in your module project. So the iterative sorts that you go through this afternoon, we won't have gone through them today during the guided project, but you'll have gone through the whole process, right? Similar to how last week went, where not everything in the module project we covered in the guided project, but we covered something very similar. again, this week especially, the focus is not so much on new concepts you're learning, it's practicing this problem solving process and getting better at taking a concept, something that you understand, and converting that into pseudocode, a plan, and then converting your plan into actual code. Okay. Let's see. All right. So let's go ahead and talk again about runtime complexity. So many of you probably remember some of the stuff we went over last week, but we'll talk about some of it again. So it can be confusing, certainly, but it is a very important topic, especially if any of you looked at that resource that's linked to in Training Kit, the Big O cheat sheet. For each of these sorting algorithms and for each of the data structures, it gives the runtime complexity in a chart. And if you don't know enough about runtime complexity to even differentiate, like which one of those is a good one, which one is a bad one, why is it good, why is it bad, that wouldn't really be helpful. So you need to know at least enough that if someone said, oh, this is O of n squared, or this is polynomial time or quadratic time, you would know, oh, that's not very good. That's worse than linear. It's definitely worse than logarithmic. So that's where you'll be at by the end of this week. You'll have enough understanding to be able to talk about the runtime complexity of your algorithms. So who remembers what's a one sentence definition of runtime complexity? So I'm going to post a message in Slack. If we could do a thread, that would be better. So go ahead and respond to the thread with a one sentence definition of runtime complexity, Big O notation. What is it? Robert, thanks. Robert says how long it takes to perform an action. Jose says the amount of operations that will happen based on the input size. Thank you. Daniel says, given the input, how many operations will it take until it's complete? Lisa says the rate of change in the execution speed of an algorithm when the data size increases. That's a good definition. Yeah. So thanks for those answers. It looks like some more are still streaming in. The most important thing to remember is it's a description of the rate of change. So it's what we're really looking at is if I have this algorithm and I run it with an input size of 10, and then I run the same algorithm with an input size of 100, what happened to how long it took to run? What happened to the speed or the number of operations that took place? Now, with constant time, we already learned, well, it didn't change. That's why it's constant. The number of times that the number of operations that will run didn't change from 10 to 100. Whereas O of n squared, quadratic, well, that went from 100 operations to what's 100 times 100? 10,000 operations, right? So that jump, that change is what we're looking at. And that's what determines the shape or the curve of the graph when we actually graph out these complexities. Okay. So one interesting thing in what I have here on the screen is most people are familiar with a standard deck of 52 cards, right? One thing that you might not realize, and honestly, it's somewhat hard to believe when the first time I heard it, is that if you fully shuffle a standard deck, so a riffle shuffle 7 to 14 times, it's likely statistically that the ordering of that deck has never existed before. All the people that have played cards, all the shuffles that have occurred throughout the world since cards were invented, that one ordering of those cards, that was a novel ordering. It was the first time that happened. Statistically, that is actually likely. Well, why is that? Well, it's because of this factorial time complexity, right? So what this means is when we're ordering cards, when you shuffle, and then you're like, if you're mapping out the possibilities for the order, like going back to probability, maybe some math that you did take. This is we're not going into complex probability by any means, but there are 52 possible cards that could take up the first slot. Well, the second slot, there's 51 possibilities, and so on. The third slot, there's 50 possibilities. Well, if you do the math and do 52 times 51 times 50 all the way down to 1, this is your answer. So this is the number of possibilities of orderings of just a standard deck of cards, right? And this is why big O or runtime complexity matters. Sometimes if you have a very inefficient algorithm, and factorial would be very inefficient, the even one number difference, 50 doesn't seem like a big number when we're talking about input size, but look at how many operations would have to occur. Let's say you wrote an algorithm that was going to print out naively every possible combination of standard deck of cards, right? Well, it would have to print this many times, even for just a normal deck of cards. Okay, so, and again, why do we need big O? It's a shared language that you can use with other developers to describe the efficiency of an algorithm. One thing that we didn't cover last week, I don't remember, was big O is talking about the worst case. And sometimes you'll hear someone say big theta, and in that case, they're talking about the average case. Most of the time when people are talking about runtime complexity, they're talking about the worst case. And one more reminder, we're talking about the number of operations, not the actual clock time of like how long the algorithm took to run, because individual variables on what machine you're on and all sorts of other things can affect the clock time. Okay. I'll give you a minute to look at this comic, and then we'll go ahead and look at some examples. I thought this was pretty funny. Are you all familiar with the comic XKCD? Let me see if not, it's got some yeah, it's fairly ubiquitous, well known, but there's some funny comics, and it's like developer engineering related most of the time. I think it's just xkcd.com if you wanted to check it out. All right, well, let's go into some examples. We went over some examples last week, but we didn't cover all of the possibilities, so we'll go over some more. So first one we'll look at is linear time. Okay, and also this time I'm going to show you a little bit more how we calculate like the unsimplified version of big O, and then what we can drop off. Or if you remember, we can take out constants, and we only care about the highest order of complexity. So let's look at linear time first. So we have this list of strings that are all animals, types of animals. And then we have this function here. There isn't a guided project linked. I can drop this code at the end. I'll put it in the notepad. It's, but for this purpose, we're not actually going to be modifying this or adding on to this code. Really, we're just looking at it together. So not a need at this point to follow along and write your own code. Thanks for that question, Alexis. Okay, so we have this list, and then we've defined a function that prints and the items of the list. So it expects a list, and it goes through basically each item in the list and prints it out. Okay, so if we were to take this and go line by line, this line here, this actual loop, this for loop, that's O of n, because it's going to cover every item in the list. And then within the loop, this is O of 1, right? This just happens once, no matter how long the input or how big the input is, okay? But when something is nested inside of a loop, we multiply, okay? You'll see sometimes we add and sometimes we multiply. We multiply in this case when it's inside a loop. Essentially, you could think of it this way, is that we're doing O of 1 plus 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 O of 1 for whatever the length of n is. Well, mathematically, that is what multiplication is, right? That's like the definition of multiplication. So, and then this gets simplified down to O of n because the constants don't matter, okay? Well, let's look at this one together, okay? So here we have a print animals function that takes a list. This for loop, again, it's based on the length of the list, so it's O of n. It goes through each item in the list. This print statement is O of 1. This variable assignment is O of 1. And then we have another list nested inside of it. And this one is not based off of the input size. It's just a constant number of 100,000. And then inside that is an increment call that's O of 1. Okay. Now what I want to show here, I'll make this a little bit bigger, that might help. But I want to show how we kind of add these lines together and then reduce it down and simplify it. Okay. So the outer loop, this is O of n. So notice how that's out here. And then whatever is inside of it gets multiplied. So that's this parentheses here. So this here maps to this, okay? But when these things are sequential, like next to each other as siblings, and they're not nested, then those get added, right? So we're adding this one plus this one. And then notice here we have this other nesting. So this for loop is right there, okay? And that, instead of an n, like if this was based off the length of the animal list, this would be n, but it's not, so that we put this constant, and that's multiplied by this, okay? So now we simplify that down, what happens? This is just basic math here. We've got 100,000 plus 1 plus 1, that's 100,002 times n, and then constants don't matter. So all of that reduces down to O of n. Did that make sense? Or was that a question that some of you had? Is I know that we had gone over that briefly, but it does help when you're figuring out this runtime complexity. Sometimes you do have to go line by line, and that's how we do it. Okay. Okay, so that is linear time. Let's see if any questions have come in. Oh. Okay, let's move on to last week I called it quadratic time. So quadratic time is O of n squared. Okay, this one. Polynomial time is like the more generic term for any of these exponents. So n squared, n cubed, n to the fourth, all of those are polynomials. So that polynomial time describes O of n squared and O of n cubed, okay? So I'm not sure why that spaced out, but okay, let's look at this one. So we have a list of all possible animal pairs. Does P equal NP? I don't know what that means, Jed. I'm sorry. No question there. Okay. So we're going to go through this line by line. So the first loop, the most outer loop is O of n. So we could write this like this, right? If we wanted to do that. Like a new set of parentheses happens anytime we're nested, right? And then we multiply everything inside of that. So we have this, that's this one right there. These are mapped. And then we also loop through every item of animals on this inner loop. So that's right here. And then inside of here, this is O of 1. So we've got O of n times 1, which happens to be O of n squared. Okay. Let's give me a second. I'm just going to take these comments off for a second. All right. So line by line here, I have the kind of summary here, but line by line, same thing for O of n cubed, right? This one is O of n. This one is also O of n. This one is O of n. And then this is a print statement, which would be O of 1 because the size of our list doesn't change how many times this runs. So again, each time we nest, we multiply. So this is O of n times n times n times 1, which is 1n cubed, which is the same as n cubed. Okay. Now this one is if you didn't track it line by line, could be a little bit tricky. Notice how we've got a for loop here and we have a for loop here. All right. So these are like siblings. They're not children. They're next to each other in the code. So that's addition. So notice here, this is for this for loop. And then this is for this for loop. Okay. And then what's for each of these parentheses inside of it, we use multiplication for the nesting. So we've got O of n, O of 1 inside, that's here. Then this, we have this cubed, we have 3 nested loops. So in this case, we get O of n plus n cubed. Only the most significant order matters, the highest magnitude here. And so that goes to O of n cubed. Okay. Now, what would be the time complexity to print quintuples or tentuples? So in this case, we're printing the triples of animals. What would be the time complexity if we were going to print the quintuples or tentuples? And I've added a thread there if you want to respond there. So the responses that I've gotten so far, we've got O of n to the 5th for quintuples and O of n to the 10th for tentuples. And that is right if we used a function like this, right? So basically for every nesting, that polynomial increases. Okay, so there's another question that's come in. So the question is, so the runtimes are only multiplied when looped and added together any other time? Yeah, that's a good way to think about it, and it's because like let's say we had 3 print statements here, right? Well, 3 print statements is going to be O of 1 plus O of 1 plus O of 1. Or you could see these 3 and go, okay, that's going to be 3 operations. Well, the reason why this has to be multiplied with the loop is because those 3 operations are going to happen however many times the loop happens. Well, in this case, the loop happens n times, right? So the loop is a repetition. The loop is doing something over and over and over and over again. Well, that is what multiplication is, right? So, and then addition, because, yeah, addition when they're next to each other. Just like you could see with these 3 print statements, those wouldn't be multiplied, those would have to be added. But that is a good general rule. Okay, logarithmic time. We'll go ahead and take a 5-minute break. When we come back, we'll handle logarithmic time, and then that'll be a good transition to go into linear versus binary search. Okay, so let's go ahead and end that timer. I'm going to set a new timer for 5 minutes. Take a brief break. And when we come back, we'll keep moving forward with logarithmic time. Our break is done. Go ahead and set a new 25-minute timer. All right. So make your way back, and we'll go ahead and continue on. So where we left off was with logarithmic time. So logarithms are one of those things that I don't actually remember dealing with too much in any of the math that I've taken or studied. The most helpful way to think about it for me has been thinking about it in terms of like inverse operations. So if we have something like 2 times 3 equals 6, and here I'm actually, I wish I could temporarily turn my linter off. I'll have to write it in comments, but I'm writing like mathematical notation, not Python. But this is multiplication. Well, what is the inverse operation of multiplication? In other words, how do we reverse what just happened? Division, right? So we can reverse multiplication by dividing. So we could we could reverse it 2 ways in this case, right? We could say 6. So our actual answer on this side, we could take that and then we divide it by one of these multiples here, and we get what we started with over here. Or we could do 6 divided by 2 equals 3, depending on what we were trying to reverse, right? Trying to reverse, okay? Well, it's the same with multiplication or addition, right? The inverse operation of addition is what? Subtraction. Thanks, Emma. So same sort of thing. We could take our answer, get 2. Okay. Well, most of you know what exponents are, and most of you even it makes a lot of sense to talk about doubling something, right? If we have 2, and then we double it, we get 4, and then if we double that, we get 8, and then if we double that, we get 16, and we can just keep going, right? We can keep doubling. Okay. Well, this process of doubling that is shown here is exponentiation, right? So another way to write this would be 2 to the 1, 2 squared. I'm not sure if you can hear that, but my youngest son sounds like he's throwing a fit, not too far away from my door. So sorry if that's loud. Okay, so we got 2 to the first, 2 squared, 2 cubed, right? Another way to think about these exponents is the doubling that's occurred, right? So in this case, we've doubled 2 3 times to get to 8, right? 2 to 4, 8, okay? Well, the inverse operation of exponentiation is logarithms. So in this case, let me show you something. Whoops. Yeah, this is a good little illustration. So basically, when we have the log of 8, when we're talking about logs in big O, we're talking about log base 2. Okay, what that means is if we have log of 8, it's how many times would we have to double 2 to get to 8? Or how many times would we, like it's 2 to the third equals 8, right? Let me see. All right, so if going back here, if we have log of 8 equals 3, notice it's like the ordering of the doubling. So log of 16 equals 4, okay? And another way to think about it is, what's the inverse of doubling something? What's the inverse of doubling? In like layman's terms, I'm not saying, I'm not looking for logarithm. We already talked about that. But what's the inverse of doubling? Halving. Exactly. Right. So you could say, if this is base 2, how many times do we have 16 before we get to 2? So we have 16, then we have 8, then we have 4, then we have 2. Well, in this case, it's like this is the first halving. I know, so I didn't quite word that right? It's kind of the same thing here, right? 2 to the 1, that counted on our steps, even though we're not doubling it yet. It's kind of the same down here. So that another way to think about it is 2 to what exponent equals 16? 2 to the 4th equals 16. Okay. So you don't necessarily even have to know all this to know when an algorithm has a time complexity of logarithmic. But this certainly helps understand, if you understand at least in general what a logarithm is, I think it's a little bit less confusing, right? So the things you're looking out for in an algorithm when you're saying, is this logarithmic time, is you're looking for a division of the data on each iteration, like some way that you're dramatically reducing the amount of data that you have to work with on each iteration. So if we look at this, we still have our animals here, and this function is expecting a list, and then it's a while loop that's checking if the length is greater than 0. What's the key where we know this is having something? Where do we see the having take place? Line 83. Yeah, this floor division operator dividing by 2. So notice each time through the loop, this syntax is written a little bit like all the logic is really chunked together in this one line. But this is a slicing of our list. Each time we're starting at the beginning of the list, but each time our slice gets shorter. Okay, so we're dividing our list that we're working with in half each time. So this would be logarithmic. Okay, let's move on and let's go to, where are you? And I can get rid of that. So now let's talk about linear and binary search. And we had to deal with this a little bit last week also when we were talking about the binary search tree. But at a high level, what would you do? Let's say I gave you a shuffled deck of cards and I asked you to find the ace of spades in the shuffled deck of cards. Is there anything you could do to make the problem easier or faster? Benjamin says order the deck. Michael says order the deck. Andrew says sort them. Caleb says spread them out face up. Have it be sorted or just go one at a time. Okay. The key here is that the only trick you can really do, right? Like humans could, yeah, we could just spread them out and then use our visual recognition and we would find it in probably less than I don't know, a couple seconds. At least in the context of an algorithm where we're talking about code like this, we're not talking about, you know, putting in an image for our computer that it can process and try to identify the ace of spades. We're talking about an actual algorithm that doesn't involve taking a picture or something like that. Can a computer really do that? Could we like spread it out on a table and look at all of them at the same time? No, like we're talking about the computer checking each one and can only look at one card at a time. Well, the only thing you can do in that case is order them, put them in some sort of sorted order, and then your algorithm could be much faster because it would know where to look, right? It would know what sorted, how you would sort them, right? If you knew that you put all your spades first and you ordered ace as 1 and you ordered from 1 to 13, then you would check the very first item in the list and you'd find it, right? But if it's unordered, there's really nothing you can do to make it any quicker. Like you literally would just have to check item by item. So if it was a shuffled deck of cards, the worst possible case every time would be that the ace came last for some reason and you'd have to look through each one. Okay. Now, what about finding a name in a phone book? How is that different? So we've got a shuffled deck of cards here, but a phone book. How is a phone book fundamentally different than a shuffled deck of cards? It's ordered, and they're ordered alphabetically, right? So if we're searching for a name in a phone book, well, that's how phone books are created. They're created with a sorted list of names where you look up the name and then you find the associated phone number. So from what we went over last week, can anyone tell me how many steps would it take in the worst case to find the name you were looking for if the phone had 100,000 names? Emma says 100,000. Robert says 17. Juana says 100,000. Now we're assuming here also my question, good search strategy for someone asked if I'm lagging. Uh-oh. Lagging, huh? Okay. Sorry about if I do cut out or anything like that, let me know because I'm the only one talking. Often I wouldn't know. So just let me know. I did a speed test right before we started, and I'm getting good internet speed. So hope it may just be on Zoom's end. Okay, sounds good now. Yeah, just let me know if something else comes up. Okay, so the question was, how many steps would it take in the worst case if the phone book had 100,000 names? Um, Robert is right. It's 17. And the reason is if we just plug into a calculator log 2 of 100,000, that gets 16.6. In this case, we would round up. So the worst possible number of steps is 17. Now you can see this another way. If we just went through the process of having the numbers over and over again, right? And see how many times it takes to get down to 1, right? So the first time we'd have 100,000, then we'd have 50,000, then we'd have 25,000, then we'd have 12,500, 6,250, all the way down. We just keep having, and that would get us down to, let's see, 782, 391, 196, 98, 49, 25, 13, 7, 4, 2, 1. Well, the number of lines here is 17, right? So the number of havings that would take would be 17. Okay. Good. So why deal with this? Why talk about linear versus binary search? I mean, people have figured this out a long time ago. You never have had to think about it up until now. What's the point of all this? Well, searching is ubiquitous in code. Comes up over and over and over again. From as simple as like a web search, like Google search, to anytime you're displaying data on a website, users expect to be able to search through it, sort it, do all sorts of interactions with it. And if you're working in like a front end framework, often you have your data stores, and you've got to figure out what you want to display. And in the process of that, you're going to find the most efficient way to search through your data, find what you need, plug it in. There's all sorts of cases where searching is important. Dealing with databases, searching is one of the areas where efficiency is the most important. Okay. One more comic taken from XKCD. This is you all this coming Christmas. All right, so let's actually start dealing with linear and binary search in code. Okay, so what our code is doing here is first we're setting a range, we're setting a size, and so this is essentially getting us a random list of numbers or integers that we're going to search through. Okay, so let's say so in this case, right, we're going to get a list of 10 integers that will be from 0 to 99, right? I think this is not inclusive, the 100. So, and we're going to search for 7. Now, a very simple, just the simple linear search function is quite simple to write. It's basically just a for loop that goes through the length of the list, and each time it says, is the current one that we're on equal to the one that we're searching for? So is the current item equal to the target item? If so, return, exit the loop. Otherwise, keep going. If we get all the way through the list without finding it, then return false. So I'm going to comment some stuff out. Oops. There. There, comment. Okay. So let's go ahead and run this. And 3. Okay. I did a bad error. Where am I at? Oh, whoops. Come on. Sorry about that. All right. So we have this list of numbers that was randomly generated, and then we looked for a 7 on that. So every time, like if we come in here and we say print and then we run that again. All right, so you can see we're looping through and we're looking at each item. And in this case, it's still 7 was not in there, so it returned false. All right, so that's a very basic linear search. And again, what's the runtime complexity of a linear search? O of n. Right. Because big O, we're talking about worst possible case. And as we just saw, the worst possible case is it's either at the end of the list or not in the list. And in that case, we have to go through every single item that's passed in. So if our array that we're searching goes from 10 items to 100 items, the number of operations goes from 10 items to 100 items. It increases at the exact same rate as our data size, which is linear. It's O of n. Okay, let's go to a binary search. So as we saw with the that guessing game last week, let's go back and look at that again. I'm sure you all remember this from last week. But our binary search method, as far as a guessing game would be, if we were trying to figure out to guess the correct number between 1 and 15, the strategy is to guess in the middle, and then we find out it's lower. So we get to, remember that concept, the logarithmic concept of halving? Well, we just went from a data set of 15 to now a data set of 7. So we roughly halved it. So now we run that same process again on half the data. We go to the middle. Okay, we just went from 7 down to 3. Roughly, we halved it. Guess in the middle. And now we got our number. And that took 4 guesses to get number 7. And again, if we take log 2 of 15 and round this up, we get 4. So how many times do we have 15 before we get down to 1? 4 times. All right. So that's the strategy, this halving and middling each time. Guess the middle. And the reason we guess the middle is because that allows us to get rid of the most possible numbers on average, right? If I just happened to guess 7 instead of 8 on the last game, I would have got it right on the first guess. But on average, or if I guess 4, sometimes I'll get lucky and get it right. But by guessing 4, I only got rid of 4 numbers. If I guess 8, I got to get rid of 8 numbers. So each guess, you're optimizing the amount of data that you can get rid of if you're wrong. Okay? So let's go ahead uncomment that. Okay, so this is our binary search method. And this is the process, and we're almost coming up on another break, and then we'll dive into this a little bit deeper. But the process you'll be going through all week. So last week, the process was, let's describe a data structure. Let's really look at it. Let's draw it out. Let's understand what's happening with all these pointers. And when we say, when we want to remove something from a linked list, what really happens? All of that work was drawing it out, understanding it conceptually, and then transferring that knowledge to your code. It's the same process this week, but instead of talking about data structures and like things that store values, we're going to be describing algorithms or processes. In this case, a lot of sorting algorithms. So things that take a collection and put them in the correct order. And it's the same type of thinking, but it's still, if it's new for some of you, that's what you'll be working on, is how to, okay, so binary search, that guessing game that I just showed you, that's not that complex. That's quite simple, actually. I mean, okay, guess the middle, get rid of half of the data. If you know, depending on if it's lower or higher, decides which half of the data you get rid of, and then you guess the middle again, and you just keep doing that, and you just keep doing that until you find the number you're looking for. Well, it sounds simple, right? And there's really not that much logic to it, but it can be difficult to then translate that into actual code. And that's where Ooper becomes really important, is don't try to write the code until you really understand what's happening. So draw it out, make the simplest possible case when you start trying to create your algorithm. Like what does a binary search do if there's only one item? What does it do if there's 2 items? What does it do if there's 3 items? Start building up your understanding of how it acts, starting from the smallest possible case or the simplest possible case, and write out pseudocode for it. And then, only then, when you really understand it, when you feel like you have a plan for how the algorithm should act, then start writing your code. And we're going to model that in a little bit with insertion sort. But right now we need to take a break. So let's take a 5-minute break. Come back in 5 minutes and continue on and look at the binary search algorithm in code. So go ahead and make your way back if you're not already. Okay, so I'm still sharing my screen. Let's set another timer. Too many things in my way. Okay, so back to this binary search. And how it differs from a linear search. So we've already understood the logic of what happens with the binary search as far as guessing the middle, reducing our data set by half, again, searching the middle. So the first thing we do is we set up a first pointer. So this would be like on the far left-hand side of our numbers. So let's say we have a sorted list of numbers, 6, 8, 9. Okay. And so first is pointing over here to this farthest or the first item in the list, the first index, and then last is the last index. And then here we're saying found is false. We haven't found anything yet. Okay. And let's go ahead and put this down here. Okay, and now here is this while loop that manages that, basically like keep doing this thing until this happens. And this, this happens of the while loop is while the first is less than or equal to last. So basically, we don't want first to ever get on the right side of last. So first is here, last is there, and they're going to be like moving towards each other in the middle. And not found. So as long as we found is still false, we haven't found it, and first is either equal to last or on the left side of last, just keep doing it. Well, what's the thing we keep doing? We get the middle. So that's on the first time it's 0 plus 4, floor division of 2. So that's 2. So that gets our middle index, 0, 1, 2. And then we check that thing if it's equal to the thing we're looking for. So if we're looking for, let's say in this case, we're going to look for 9, right? 6 is not 9. So this won't happen. So we didn't find it. So what's the next thing we need to do? We need to check if this is less than, or if it's less than, if the thing we're looking for is less than our guess, then what does that mean? So if we just checked this middle and it's 6, but we're looking for 9, what do we know in a sorted list? What does that mean? Is 6 too early in the list or too late? Like, is it too far to the left or too far to the right? Yeah, it's too small. Our list is sorted in an ascending order. So if we check the middle and say, oh, 6, well, we're looking for 9. So everything from here back can't be it. Just like in that guessing game, we crossed out everything before it, right? All the numbers before it couldn't be it. So in code, what does it look like to eliminate 6, 3, and 1? Well, in this case, right here, it means taking our first, remember we have our first pointer and our last pointer, and moving it one ahead of this. So basically by moving our first pointer now to 8, now the thing we're searching is 8 and 9. That's it. We have first here and 9 there. Okay. And now we're still in this loop. First is still less than or equal to 9, and we still haven't found it. So now we have first as index 3, last as index 4, add those together, floor division of 2. What's 7 divided by 2? It's 3.5. Round down, it's 3. So we're going to look at 3. This index, is 8 equal to it? No. And so we come down here. Again, 9 is still higher than this one, so we can get rid of that. And then we move our first pointer here. So now first and last are on the same one. We come back through. We get our middle, which is 4 plus 4 is 8, divided by 2, floor division, that's 4. And when we check, it's going to be found equals true, and we'll return true. Okay. So again, I want to show you something that can be really helpful. If you're getting code, you've written code, but you're having a hard time tracking it in a way that's helpful to you, close out of this. You can use a Python tutor visualizer. You can use your VS Code debugger, okay? But I could do that same exact process we just did in like trying to understand it line by line in my code. And I could do, what did we use here? We had 13689. So 13689, and we're going to look for 9. And now we can run this. And we can just walk through it step by step. It will show us the same things, right? But it might be easier to keep track of what's happening, right? So first is 0, last is 4, right? We go through here and do the exact same thing, but we can track and see what these variables are. Okay, so if you had trouble tracking that last when I was just walking through it step by step in the code, and then this afternoon when you're working on your own solutions, don't hesitate to use Python Tutor. Use something that can help you visualize line by line, especially if you run into bugs or things where it's like, that should be working. From my logic, that should be working. Usually what happens is you've written a bug and you didn't catch it. Okay. If someone asks a question, is this example a standard template to writing other linear searches? Linear search is just so simple as far as it's just looping through each item and checking if it's there, like checking if you found what you're looking for. And in this case, we wanted to return a Boolean if we did find it, and false if we went all the way through the list and didn't find it. So I wouldn't say it's a template, but especially in Python, there's only so many ways you could write this. And that being said, binary search, like you could write this differently, right? You could write a binary search that works exactly the same way, but the way you check this might be different. Like maybe you check if it's greater than or equal, and then these are swapped, something like that. Okay, so where we're at is right here, classic iterative sorts. So this is our last agenda item for the day. And this is where we'll actually start to build out an insertion sort algorithm together. And you'll see that whole process, U, P, and E, and that's the exact process you're going to use this afternoon. So how do you organize a hand of cards? Another card example, but if you're playing a game of cards, do you pick them all up at once and then kind of rearrange them as you go, like in your hand? Do you pick one up at a time and then you have your one and then you pick the next one and put it in the right location? And then, yeah, some people are saying explicitly the way they would order, and the way you order your cards might depend on the game. The values of the cards in Pinochle are different than the values if you're playing blackjack or poker or rummy. Yeah, the way you would order your cards in rummy might be totally different. But the point is that there are lots of ways you could sort something, right? Like if you just went to a bookcase that was completely unordered, unsorted, right? It wasn't like a library that had a Dewey Decimal System or some way that the books were organized. It was just your personal library. It was totally unorganized. Like the actual processes you could go through physically to like reorder the books could be totally different, right? And computer scientists and people that work with data in computers have been thinking about this stuff for a long time. And there are basically these classic ways of sorting data that people have known about for quite a while. And like, why learn about them? Why should you learn about these classic sorting methods that, like you're not covering new ground here, right? Like you're not going to like, this isn't doing some sort of cutting edge research where you're discovering, hey, I by knowing insertion sort, now I'm going to like invent some new sorting algorithm. The reason that we make them a part of the curriculum, the reason why you cover them, the reason why you're required to go through this process is it's kind of like data structures last week. Like it will prepare you for interviews potentially. Like some of these questions about these things could come up in an interview. It's like considered like a common amount of knowledge that you should know as a developer. But more importantly, they're like really defined problems. They're like really well-defined problems, like a sorting algorithm, like the way to do an insertion sort. You could describe what that means in a few sentences, and you'll see that in a second. But going through the process of taking a couple lines that describe the process of insertion sort and turning that into code, like that might actually be really hard the first time you do it. But the more practice you get, the more reps of doing that over and over again, you'll become a better programmer. And that process of going from conceptual knowledge to actual code will get cleaner and cleaner and quicker and quicker and easier and easier. And that's what we're working on. That's what we want you to develop. That's the muscle that we're building right now. Okay. Another comment before we dive into insertion sort. All right. Whoa. I'm having SQL flashbacks, right? Okay, so the first thing we'll look at is we're at the understand phase of insertion sort. So there's a couple things like for these classic sorting algorithms that are well known, right? You could just Google insertion sort, and like you could see a bunch of stuff comes up. You'll probably find some videos that show an illustration of how it works. If you go to a Wikipedia article, you'll probably find some good background information. Hopefully you can find like a pseudocode implementation. You could probably find like a verbal description of what happens. You can see here, there's an animated GIF that shows what it does. Like there's no shortage of ways that you can try to understand what the algorithm that you're looking at is doing, okay? The important thing is you stay on this step. You stay on understand until you really get what is happening. Like what it's almost like, and sometimes it helps if you actually take physical items. This might seem a little bit silly and you might even feel silly doing it, but like in this case, you could actually take little slips of paper or sticky notes and write numbers on them, put them out in an order like we see on the screen here, and try to implement an insertion sort physically. Like what do you do to go through an insertion sort? Okay. So let's do that now as far as just understanding what an insertion sort is. Okay. Let's see if I can make that a little bit bigger. Okay. So the first thing to notice here is in the pseudocode that describes an insertion sort is it says mark the first element as sorted. Okay. Simple enough. The concept is any list of one item by definition is sorted. It can't be out of order. There's only one thing. So the first step is just to say, we're going to count this as already sorted. So this is our sorted list. This is our sorted list. And then this is our unsorted list. Okay. So we've got two different lists in our mind conceptually that we're dealing with. Okay. And then what's the next line? For each unsorted element. So now we basically started a for loop that's going to be on this unsorted portion of our list. Okay, so that you see this is just one outer loop, the for loop of the unsorted portion. Okay. And this is pseudocode. So it says extract that element. So let's look at that first item that we're looping through. And then what do we check next? Or so we say, then we start another for loop. And we set a variable j. That's the last sorted index down to 0. So now we're starting a loop in the sorted where we start at the end of the list and work our way backwards. You'll see that in a second once we have more items, okay? So that's where we are here. So we're going to start a loop here and go that way. And it says if the current element j is greater than x. Is 3 greater than 44? No. 3 is not greater than 44. So we don't go into this here. We don't go into the if. It says break loop and insert x here. So we'll see, we'll eventually go into this if and you'll see it. But so now our sorted portion of our list is here and our unsorted is right here. Okay, right? This is in order. 3 comes before 44, so that's right. So then we keep our outer for loop going. Now we're on this item 38. So we look at 38, we set, and now we have our other for loop that we're going to go this way. We're going to start at the end and work our way back. Okay. And so if the current element, so if this is greater than this, we have to move the sorted element to the right by 1. Right? So we're going to be able to shift these things over, right, until we have a good spot for this. So now we're back. We're going to do one more check. Is 3 greater than 38? Nope. So we don't need to shift it, and we can insert that right here. You can see now our sorted portion of our array or our list is growing, and the unsorted portion is shrinking. So we're just looping through these items, and then we're finding where we're going to insert it on the other loop. So again, 44 is greater than 5, so we need to shift it over. 38 is greater than 5, so shift it over. 3 is not greater than 5, so don't shift it and insert the 5, right? And we just keep doing this. Shift if it's greater. If not, that's the spot to insert it. Shift if it's greater. If not, insert it. And just keep going through, right? We just keep doing that. So it's not a complicated algorithm. It's like if you had a card of hands and you were picking one, and each time you just went and checked right, like from the right side of your hand over, and just checked each card until you found the right spot and inserted it there. Kai is asking about the efficiency, and that's a good thing to start to wonder. It feels very inefficient, right? Like, look at all this shifting happening. As far as complexity goes, what state would our list have to be in initially to be the worst possible case, right? If you look again, whoops. Reverse order, right? Yeah, if it was reverse order, then we're having every insert, we're having to shift every single item over. So we're doing the maximum possible number of computations, okay? Any ideas? What are our guesses about efficiency? Just looking at it, we don't have code to look at. We can't go line by line, but just going through this, seeing the pseudocode, what do we think? Mandy says quadratic or polynomial, O of n squared for worst case. Any other guesses? Do we think that's right? A lot of people agreeing with Mandy. Yeah, we've got this outer for loop that has to go through each item in the list. And then we've got the inner for loop that at first, right, it's only going through like one item, then it's going through 2 items, then it's going through 3 items, then it's going through 4, then it's going through 5. Well, that would be considered O of 1/2 n, because on average, it has to go through half of the list each time on the inner loop. Well, remember, we get rid of our constants. So it's n times n, which is n squared. Good. So you guys got that. Okay, so understand phase, right? Like we've got conceptually what's happening here. I think we're good there. The next step you would go to is you would write out pseudocode. So we've got some pseudocode here that we could start with. Let's try to write our own. Wow, the blank page, the most intimidating thing of all. So let's get started. We'll do insertion sort, and we expect a list, an unsorted list. Okay, so and now I'm just going to put pass there, and then we'll start describing what's going to happen in pseudocode. So what was the first thing that happened over here? So what is this step? What happened right there? CC says grab the first item in the list, marked as sorted, define the first element as sorted, mark first index as checked. Right. Okay, so conceptually, mark first item as sorted. Okay, now what that means, right? I don't really know yet. Like mark first item as sorted, separate first element. Like we don't really know what we're going to do yet in code, but we know that we can consider the first element sorted, right? Now what's the next thing we need to do? Let me see if I can this on one screen. Go. Okay, so we've got this part. We've got the marking the first thing as sorted. What's the next thing we need to do? What happens next? What's like the main operation that this thing has to do? Yannick says checking the value of the sorted versus other values. That's part of it. So we're starting to think about comparing the next element to the sorted item. But even above all that, like before we start comparing, what do we have to do? The main loop that runs in this function is like the reds being separated out. Notice how it's just slowly going through and checking each item. That's the main kind of functionality of the function, the like the primary thing that happens. And so basically that would be what? How do we loop through all those items? Got quite a few people typing. I'm just waiting to see what comes in on Slack. Slice the remaining list, select the rest of the list. We've got a while loop. Okay, lots of good ideas. And right now we're thinking in pseudocode. We don't even need to know how we're going to write it in Python. We can write something simple like for every item after the first index, or after the 0th index. Like that's really all we're saying is like we get to skip the first one because it's sorted. And then for each of these items, we're going to do something. I don't know what we're going to do yet, but I know we have to at least hit every item on that list on the right side of on the first thing of the first item we checked, right? Okay, let's take another break. We'll do a 5-minute break. And when we come back, we'll keep building out pseudocode and we'll actually have plenty of time to write out code. And we'll have time to preview what is expected in the module project this afternoon. So we're making great progress and have plenty of time to finish all we need to today. So let's do another 5-minute timer, take a good break, and be ready to finish strong when we come back. Sorry about that. I was muted on my actual hardware. Last break is over. Our final break. We've got about 20 minutes to go ahead and continue writing pseudocode and then code for our insertion sort. And then at the end, we'll go over the module project for this afternoon. Okay. So where we were at is we were writing out pseudocode. So we figured out that for every item, let's word this a different way. Instead of after the 0, for every item starting at the first index, or let's say second element, okay? That's how we've described it previously, okay? So we've got that part down. We know we mark the first item as sorted, then we loop through these. Now for each time through, right? So we mark that. So now we're on this item in this for loop. When we have 44, what do we do next? What are we going to do with this 44? Compare it, okay. Caleb said save it in a temporary variable. That's a good point. Okay, so let's start there. So we're going to put current item in temp variable. So we need some way to keep referring to this item. Okay. And then what other people have said is comparing it to sorted. So when we compare it to the sorted portion, what kind of process is that in our code? Like when we're right here and we compare 2 to this list, right? What are we going to have to do? Like, isn't this also kind of like a loop, like our outer loop? Okay. So another for loop, iterate backwards through the sorted list, compare and do something, right? Yeah, we're going to do this. Do you think that, so we had a for loop here for our outer loop. Do you think we should use a for loop for the inner loop or some other type of loop? And we don't necessarily need to decide that yet. We're writing pseudocode, but you could start to think like, are those loops going to be the same or is there something a little bit different about those two loops? But we have a temp variable. Now, how would you describe this? Like when I think about it, like, and with pseudocode, we can actually use words like how we describe what we would physically do. So we could say something like look left until we find where it belongs, like where it should go. Okay. And then like in that looking left, so while we're looking left, we need to do what? Like what happens on this one? What was that? How would we describe what happened right there? Yeah, so there's a comparison. Okay, so look left until we find where it belongs. So to find where it belongs, we need to compare current item to, I don't know, let's call it sorted item. And we could say when do we have to shift it? So this is sorted item. This is current item. Sorted item has to be bigger or smaller than current item. So, right, yeah. So current item is this one, 38. So 38 is smaller than 44. So we shift it over, and it depends on how we want to word that and how we want to check it. I would probably say if sorted item is bigger, shift it rightward. Okay. A little smaller. Oh, it's probably too small. Okay. So if sorted my item is bigger, we're going to shift it rightward. And then what do we do once this is not true? Like, so we're looking left until we find where it belongs. And then what do we do? Oh, Andrew, good question. Are there two lists here or is it just one? Well, we haven't really said because because we are working in pseudocode yet. We haven't got to that implementation step, but it's good to start thinking about that. In this implementation here, this visualization, does it look like we're dealing with two different lists, or are we dealing with one list that we're just kind of moving stuff around within that list? Mandy says one list. Neil says one and moving indices. Yeah, we're dealing with what we're going to act as though we're dealing with one list, and we're like moving values around within that list. Okay. And then there was another question. CC said shift what rightward? Good question. So if sorted item is bigger, shift sorted item rightward. Okay. Maybe we could put it like that. Okay. And the last question that I asked that we haven't got an answer to yet is like, so when we're done looking left, so we looked left and we said, hey, is the sorted item bigger? Nope. So then what did we do next? What's the very next step? Well, if we're dealing with a while loop, and we're not at the beginning of the sorted list, yeah, we would update the index of the sorted item and we would keep looking through. But in this case, we needed to insert, I guess is what I was going for, but I wasn't super clear on that. So sorry. So we either compare the next item, right? We move that list or that loop over one and we keep going through, or we insert the item once we get to where it belongs. So insert item. So we're assuming there that like once that, what are the conditions that we know? What are the conditions for when we insert the item? So we're either, there's two places we could be. So if it's greater to the item to the left and less to the item to the right, we're not dealing with right though. We're never going to compare to the right. So if it's greater than that item, or so if current item is greater than sorted, or we are at the beginning of sorted. Insert item. Okay. Stop doing that to me. Okay. So I would say this is a pretty good spot to end in our pseudocode. Like, you could probably work it out a little bit better. You could maybe add more verbiage or be more clear. I think at this point for me in my process, I would probably start trying to write code. Okay. So let's do that now. The first thing I wanted to mention is sometimes you write pseudocode that then when you actually write it, like implement it, it doesn't need code. Right? So with that in mind, like if we're only working with one list, we're not going to create a new list. What Python code would we write for line 3 and 4? Like how are you going to mark the first item as sorted? Neil says nothing. You could just start at the second element. Seems like a good idea. Any other ideas? Caleb included a code snippet that starts the outer loop, right? Yeah, so we could just say no code needed here, conceptual, right? We'll leave that for now. Like when we're done, we might even just remove that comment because it's not necessary, but it still helped us with our plan. Because here we know, okay, we're going to have a loop. So we could say for I in range, and the range starts at 1. So this basically fulfills that requirement of our plan. We're saying we're going to mark that portion as unsorted because we're starting at, or as sorted because we're starting at 1. Okay. And then the length of our unsorted list would be correct. And one thing I noticed right away is when I saw the code unsorted list, it actually kind of confused me because in our plan, we were talking about like the unsorted portion of our list. And so I might, like, to avoid confusion, I might even just call this like input list. Because I really don't want to like keep trying to remember, okay, am I talking about the unsorted portion conceptually or the input list? So let's just do that to avoid that. So we have our outer loop. How do we put the current item in a temp variable? What does that look like? What would you put in code to do that? Okay, that would work. Yeah, we could call it current item. And I even like to be more verbose. Some people don't, but I don't mind writing out the whole thing just so I can read it. but we have our input list and I. Okay, so that's basically like what we just did is like this step. It's like marking the current item that we're on. Okay, now we're to the look left portion. What is it? So what's the item that we're going to start looking left at? Like even if we get further down the road here, let's see here. So we have current item is this, and then this is like the first item we look to the left. How can we mark this item? Like what if we wanted to mark that item to start our loop? What would that look like? Jojo says it's basically whatever the current item index is minus 1. It's just 1 to the left of it. Okay. So Caleb dropped a for loop. We could use a for loop here. That's certainly fine. I'm going to choose a different loop here, but again, all of these implementations, all of these sorts, like it's totally possible and more than and fine and would be expected that your implementation look a little bit differently than someone else's. In fact, if it looks exactly the same, then I might think something was off. Okay, so let's say I don't know what I want to call this. Let's call it our look left index. Sure, let's call it look left index. But that would be what? I minus 1, right? Okay. So now we have our look left index. And we said earlier, a few people thought of using a while loop here. And a while loop makes sense because we're essentially checking a condition, right? And this is where our pseudocode might not end up being in the exact order of our code when we look at our whole plan. But this logic here we could basically use in our while loop, right? So we know if our look left index, how do we know if we're at the beginning? What would the look left index have to be at the beginning of the list? What would it have to equal? 0. Okay. So as long as we're not at the beginning, so that means greater than 0, right? And what was the other thing? What was the other thing? The current item is greater than sorted. That's how we know we need to insert it. But what's like the opposite of that? So that would mean current item is less than. Yeah. Is that right? Current item is less than. What are we comparing it to? How would I get that? In code, how would I get a reference to this item? Not sorted. Okay, there we go. Yeah, because our input list, our look left index is 1 less than the current one, and then we're going to end up updating that in our while loop. So we have something like this. So while those conditions are true, we're going to enter this loop. And so now we could probably clean up some of this. Find where it belongs. So let's actually change this to say, if current item is less than sorted, and I'll put it in a different order. So if we are not at the beginning, and current item is less than sorted, right? That's what we're checking here, right? Caleb, that's a good question, but I think you'll see it depends on where we decrement our counter, right? We will actually get to the first item. You'll see it in a second, but that's a good question. I think I'm right here. So let's just keep going. I don't want to change it, but that is a good question. So we've already done the comparison here. Like this is the comparison. So we don't need to compare inside here, right? Because if we've gotten in here, that means the current item is less than the one to the left. So what did we have to do if this is less? What's the next step? It says shift the sorted item upward. How would I shift an item? No, that wouldn't shift anything. That's just the index. How would I shift an item? Okay, you'd swap. We don't actually need to swap in this case because we have a reference to, like, that's why we got the temp variable. So we can actually notice here, like, I hope the visualization is clear, but that, it looks like a swap, you know, the way they visualized it, but this is actually just overwriting what was there before it. Okay, so basically we would just go, yeah, this is where you see like a +1. This is where you would have a +1 in your code, but you would basically have input list, and we want to take the thing that we're looking left at, and we want to move it where? We want to move it up. We want to move it to the right. So then we would do input list, look left index +1. Oh, I'm sorry. I have that swapped. I'm sorry. My assignment was swapped. Right? So we're taking, so if we go back here, we're looking left here. This is the look left index. We say what is here is look left index +1. Take that and put it over there. And that's what we do. Okay. And then what's the final thing we need to do is now we need to decrement. Okay. So we'll keep going in this while loop as long as we're not at the beginning and the current item is less than the one to the left of it. Okay. And if we exit the while loop, then these conditions are true, basically. We don't need to have some sort of if or conditional in here because that's what this is. Then we insert the item. So what does that look like? So we go input list, our look left index, and that will equal the current item. And so that's our for outer loop. And then once we do that for all the items in our list, we return the input list. Whoops. Okay. So might clean that up a little bit, but that's essentially an insertion sort. So you you went through that whole process with me as far as going through line by line, understanding what an insertion sort is, writing out pseudocode, and then turning that pseudocode into code. Okay. It's not an exactly linear process. You saw that the way we structured our pseudocode, you couldn't just kind of swap it out line by line. Sometimes you did have to modify the ordering of things a little bit, but that's the exact process you'll go through in the module project. So, and I know we're 5 minutes over, I apologize. Just about another minute or so and we'll be done. But here's your module project. There's clear instructions here. Basically, you open up this directory, okay, and read through the descriptions of bubble sort and selection sort. So those are here. You may also do some like Googling, some your own research, look for visualizations during that understand portion, and then implement your own versions of those. So you come in here, you've got selection sort, you've got bubble sort, and there's a stretch. So if you get through these easily, go ahead and tackle counting sort. Run your implementations through the test files, and then you also implement all the methods in the searching file. So a linear search and binary search from earlier, you should implement those. Those were fairly simple. And make sure those work by running the test files. And that's it. That's it for this afternoon. So it's not a lot, right? I would expect, again, you would, all of these, like you're probably looking at maybe 40, 50 lines of code. So it's not a lot of code. But it is like, you'll see as you start to dig into it, sometimes when you conceptualize it, there is a little bit of a break. Like, okay, now I've got to turn this into code. I've got to turn this into a plan. I've got to turn this into pseudocode. That's to be expected. So if you hit that wall, if you're struggling, go back to the understand step. Go back a step. Make sure you really understand what's happening. Have a visualization open. That Visual Go tool that that I was using, it's visualgo.net. It looks like they have, for bubble sort and selection sort, they have visualizations. Those may be really helpful to you. Okay. With that, we're 7 minutes over. I apologize. I try to end right on time. I know your lunch is very important. So we'll go ahead and end here, and we'll see all of you in the help channel, and we'll see you tomorrow in the guided project. Good luck this afternoon.